Welcome to Center of Math's series on graph theory. We're going to talk a little bit about isomorphisms and connectedness. So an isomorphism of a graph is, if we have two graphs, it's a bijection between the vertices that preserves incidence between the vertices. So these two graphs are isomorphic. If you can see these three pieces here kind of line up with these three pieces here. This one just goes over here. An isomorphism of a graph, you can think of it if you can just kind of move the vertices to each other in some way between two graphs, they're isomorphic. But to be exact, it's a bijection that preserves incidence between two graphs. One thing to note about isomorphisms. So one thing to note, if we have two graphs, the degrees of vertices are preserved by an isomorphism. So we have some isomorphisms, the degree of v is the same as the degree of wherever vertex the isomorphism sends that v2. And this isn't too hard to see. It follows from, so you take any vertex v, it has some number of vertices it has edges to. V gets sent to theta of v, or wherever your isomorphism is, and consider all the vertices it was adversely connected to. They also get sent to some other vertices, and because it preserves incidence, these vertices are all still have edges to the image of our original vertex. So the degree will be at least as big as our original degree, and it can't be any bigger, because if it did, we'd be sending a vertex that originally had no connection to it to a vertex that had a connection to it, which is not an isomorphism. One thing to note, if we have two graphs such that the degrees, we can send vertices to other vertices such that degrees do match up, they are not necessarily isomorphic. So a counter example. So note that this graph, the degree of each vertex is in fact 2. They're each connected to other vertices. And this whole thing, this is one graph. It's just not connected. This is one graph as well, and note that every vertex is also of degree 2. But we cannot establish an isomorphism between these two, because any isomorphism from this to another graph, you have two components over here, and we need to find components. We have two different sections. If you send an isomorphism of this graph to any other shape, these four will still have paths between them, and they will not have paths to this section. Whereas here, you have paths to any vertex. So these are not isomorphic, but they're a set of vertices. You can have some map between them such that a vertex with degree 2 gets sent to a vertex with degree 2, but they are not isomorphic. So we say a graph is connected if between any two vertices we can find a path. So this is kind of an intuitive definition. We can just go from any vertex to any other vertex, so everything's connected. Component is a graph such that it's not strictly contained, a connected graph that's not strictly contained in any strictly larger connected graph. This may seem familiar if you're familiar with topology. Kind of similar to that definition, as it's the largest section of a graph that you can get from any vertex or any other vertex. Just a quick example. If we consider these two squares are a graph, the components of this graph is just this square and that square. If we take these four vertices and add any other vertex to them, it's only not connected. If we remove any vertices from it, any subset of vertices, we can find a larger connected graph. So these two, and same for the right square, these two squares are the components of this whole graph. So just an example of that. So one thing we can prove, if we have a graph G, where G has order n, and for any vertex in the graph G, the degree of v is greater than or equal to n minus 1 over 2, then the graph has to be connected. So we can prove this by contradiction. Assume the graph is not connected, so we have at least two components. Note for CI, we're going to say CI is a set of a component that's our vertices in our component. We have so many components, at least two components, and we're going to sum over all the magnitude, the amount of vertices in each component and we're going to sum over all our components. And note this sum of all our components will give us all the vertices on the graph, so it has to equal n. Now, if we say all of these magnitudes is greater than or equal to n plus 1 over 2, we have at least two of these. So summing that, the sum is going to be greater than or equal to n plus 1. But n plus 1, that's greater than n. So that's impossible. So at least one of the CIs must be strictly less than n plus 1 over 2. And so in this component, so we have less than n plus 1 over 2 vertices. Take any one vertex, v in CI. So we have less than n plus 1 over 2 vertices in some CI. Take one vertex. There are n plus 1 over 2 minus 1 vertices for this one vertex v in CI to connect to, so n minus 1 over 2, strictly less than n minus 1 over 2 vertices for v to connect with. And so the degree of v must be strictly less than n minus 1 over 2, which is a contradiction. So that proves our theorem. So if all the degrees of v are greater than or equal to n minus 1 over 2, our graph must be connected. So one more definition. If we have a connected graph G, an edge is called a bridge if G without this edge is disconnected. And with that, we can prove a necessary and sufficient condition for an edge to be a bridge. So we can prove an edge is a bridge if and only if it is not part of any cycle. So first, let's assume we have an edge that is part of a cycle. So if we have two vertices in a graph, something's going on, and these are part of a cycle, and we assume our graph is connected. So between any two vertices, we have some path, A0, A1, AN. So in this path, let's say we use this edge at some point. If we remove the edge, we can always, in our path, just replace it by because it's in a cycle, we have a second path, we can just replace this path by. So then that shows that any path between any two vertices that we had because it was connected, we still have a path between any two vertices, and so the graph is still connected if it's part of a cycle. Now if we assume this edge between two vertices and there's something going on with the graph outside, we assume these two vertices are not part of any cycle. Yeah, so we're going to assume they're not part of any cycle. We're going to remove the edge. And let's say this graph is still connected. So if we take V1 and V2, there's still some path between these two. So that means even without this edge, something else was happening in the graph that allows us to take a path from V1 to V2. But now we can form a cycle, taking this path and combining it with our edge, and so they are part of a cycle which is a contradiction. So there cannot be another path between these two. And so if they're not part of a cycle, then they are a bridge. And that should prove both directions of this theorem. And that's it. Thanks for watching. If you like this, please check out our other graph theory videos. Check out centermath.org and follow us on Facebook and Twitter. Thank you.